In 1974, we aimed a radio telescope at star cluster M13, and we transmitted humanity's first intentional message to aliens. It was ceremonial. M13 is 25,000 light-years away. But what we didn't anticipate were the closer neighbors who might have already been listening to our accidental broadcasts. Indeed, for 123 years humanity has been talking to the universe, talking without permission. Every baseball game broadcast, every sitcom transmission, every planetary radar ping, all of it bleeding into space, creating an expanding bubble of human chatter. Then, starting in 2017, mysterious interstellar objects began visiting our solar system. Oumuamua, Borisov, now 3 Atlas, each one stranger than the last. What if our century of electromagnetic chatter finally reached a listener? What if these aren't natural phenomena? What if they are the universe's way of saying, message received, stay until the end, to discover how our cosmic conversations might finally be getting replies? Now prepare yourselves. We begin shouting into the dark. For over a century, humanity has been talking to the cosmos, not by choice exactly, but talking nonetheless. Every AM radio station broadcasting baseball games into the night, every television tower beaming sitcoms skyward, every planetary radar pulse we fired at Venus or some wandering asteroid, all of it bleeding into space at the speed of light, creating an expanding bubble of human chatter that now extends roughly 130 light-years. We call this our radio bubble, a sphere of electromagnetic noise that announces our presence to anyone listening. But there are 2 kinds of calls we've made into the darkness. The first are accidents, radio leakage, the unintentional spillover from a civilization that learned to manipulate the spectrum before we learned to be quiet about it. The second kind are deliberate messages in bottles thrown into an ocean we can barely fathom. In 1972 and 73, we launched Pioneer 10 and 11. They carried golden plaques depicting naked humans and pointing toward our location. Optimistic, perhaps naive. The plaques showed the hydrogen atom's spin-flip transition. This provided a universal unit of time and distance. They mapped our solar system and indicated Earth as the 3rd planet from a medium-sized star. Most boldly, they included images of a man and woman standing beside the spacecraft for scale. Their hands were raised in what we hoped was a universal gesture of greeting. The Voyager Golden Records followed in 1977. A more ambitious attempt. Chuck Berry's Johnny B. Good spinning through interstellar space alongside whale songs and greetings in 55 languages. The records contained 116 images showing the diversity of life and culture on Earth. They included mathematical definitions, the solar system DNA structure, and human anatomy. Carl Sagan called it a message to the universe. Others called it cosmic graffiti. But the most focused shout came from Arecibo in 1974. Frank Drake and his team aimed the giant dish at the globular cluster M13, and they transmitted exactly 1,679 bits of information. Why 1,679? Because it's the product of 2 primes 23 times 73. Anyone receiving it would recognize this mathematical hint and arrange the bits into a grid. The message would reveal itself as a pixelated diagram. It showed our number system, the structure of DNA, a crude human figure, and our solar system. The transmission lasted exactly 3 minutes and used nearly 1,000,000 watts of power. For those brief moments, Arecibo became the brightest radio source in our local galactic neighborhood. The signal raced toward M13 at the speed of light. It carried humanity's first deliberate attempt at interstellar communication. It was ceremonial, really. M13 is 25,000 light-years away. By the time our message arrives, human civilization will have risen and fallen several times. But we sent it anyway, because sometimes the act of calling matters more than the expectation of an answer. Giuseppe Cocconi and Philip Morrison had already shown us the logic in 1959. Writing in Nature, they argued that radio waves would be the universal medium. They pointed to the waterhole, that quiet region of the spectrum between two frequencies. It's bounded by the emission lines of hydrogen and the hydroxyl radical. Any civilization that understood chemistry would know to look there. The hydrogen line at 1420.4 MHz became particularly significant. This frequency represents the energy difference when a hydrogen atom's electron flips. It's the most abundant element in the universe undergoing its most fundamental transition. If aliens wanted to establish a universal communication standard, hydrogen's signature would be the choice. Our own searches have followed this reasoning for decades. The SETI Institute's receivers scanning the hydrogen line. Breakthrough, listen, monitoring millions of stars across multiple frequencies. The logic is sound. If you want to be heard across interstellar distances, you broadcast where the galaxy is quiet. But here's what we've learned about our own transmissions. They're surprisingly hard to hear. Most of our television and radio signals become indistinguishable from background noise within a few light years. The inverse square law is unforgiving. Double the distance, quarter the signal's strength. Only our most powerful transmissions survive the journey to nearby stars. Planetary radar systems like Arecibo's or Goldstone's shine bright enough to be detected. These systems, designed to map asteroids and planets, accidentally serve as lighthouses. Their beams sweep across the cosmos every time Earth rotates. This creates a distinctive signature that would be unmistakable to any monitoring civilization. The Deep Space Network represents humanity's most sophisticated attempt at cosmic communication. 3 massive antenna complexes maintain continuous contact with our robotic explorers. These dishes, some stretching 70 meters across, could detect signals from the edge of known space. Our spectrum would look peculiar. Narrow carriers appearing and disappearing as our planet rotates. The structured emissions of FM radio and television. Brief, intense radar pulses sweeping across the sky in regular patterns, all of it clustered around a small blue planet that seems unusually active in the radio bands. The International Telecommunication Union protects certain frequencies for radio astronomy, recognizing that some bands must remain clear for us to hear the universe. Radio quiet zones around major observatories restrict terrestrial transmissions. The National Radio Quiet Zone in West Virginia spans 13,000 square miles. It creates an oasis of electromagnetic silence around the Green Bank Observatory. The United Nations Office for Outer Space Affairs coordinates international space policy. Though they've never had to deal with incoming mail, their mandate covers the peaceful use of outer space. But the frameworks assume human actors operating under terrestrial legal systems. No one has seriously considered how international law might apply to visitors from other star systems. This brings us to a fundamental tension in the SETI community. Traditional SETI has always been about listening, passive reception. Breakthrough Listen processes petabytes of data from radio telescopes worldwide. The SETI Institute operates the Allen Telescope Array in Northern California. But there's another camp, active SETI, sometimes called METI. These scientists want to transmit powerful intentional messages into space. They argue that if everyone just listens, no one will ever hear anything. The galaxy might be full of civilizations all waiting quietly for someone else to make the first move. Their proposals raise uncomfortable questions. Export control regulations treat high-power transmitters as potential weapons. Radio systems capable of interstellar communication could theoretically be used for military purposes. And then there's the deeper philosophical problem. Who gave us the right to speak for Earth? Should such momentous decisions be made by small groups of scientists and engineers? The history of false alarms keeps everyone cautious. In 1967, Jocelyn Bell Burnell, detected an incredibly regular radio signal from space, one pulse every 1.337 seconds, precise as an atomic clock. The Cambridge team briefly considered the possibility of alien intelligence. They even called it LGM-1 for Little Green Men 1. It turned out to be the first known pulsar, a spinning neutron star whose radio beam swept past Earth like a lighthouse. The precision wasn't artificial intelligence, it was physics operating at extremes. Neutron stars pack more mass than the Sun into a sphere barely 20 kilometers across. Their magnetic fields are trillions of times stronger than Earth's. When such objects spin rapidly, they create cosmic beacons of extraordinary regularity. Then there's the famous WOW signal detected in 1977. For 72 seconds, the Big Ear Radio Observatory recorded an incredibly strong narrowband transmission. The signal was so striking that astronomer Jerry Eman wrote "wow" in the margins. The transmission showed characteristics that SETI researchers had long predicted for artificial signals. Despite decades of follow-up observations, we've never detected it again. Theories abound: a one-time transmission, a reflection of an Earth signal, or some unknown phenomenon. The signal remains one of SETI's greatest mysteries. But it is also a cautionary tale about the challenges of distinguishing artificial signals from cosmic noise. These experiences taught us valuable lessons. Extraordinary claims require extraordinary evidence. Any candidate signal must be repeatable, detectable by multiple observatories, and verifiably extraterrestrial. The field has developed rigorous protocols for verification and announcement. The Rio scale, similar to the Richter scale for earthquakes, provides a framework for evaluation. Ratings from 0 to 10 consider both the signal's apparent artificial nature and its potential impact. A confirmed signal from an advanced alien civilization would rate an 8 or 9. Popular culture has shaped our expectations too. From Orson Welles' War of the Worlds to modern films like Contact and Arrival. We've been rehearsing first contact scenarios for generations. Science fiction often portrays alien contact as dramatic and immediate, but real SETI focuses on more subtle possibilities, faint signals, archaeological evidence, or technological artifacts drifting through space. But here's the thing about shouting into the dark. Eventually you start to wonder if anyone is listening. We've been broadcasting for over a century now. Our radio bubble continues to expand, carrying the sounds of human civilization to nearby stars. Every year, our electromagnetic signature reaches new solar systems. If someone out there has been paying attention, they would have had decades to prepare an answer. The physics are straightforward. Signals travel at light speed, so responses from nearby stars would arrive within decades. The question that keeps SETI scientists awake at night isn't whether there's intelligent life. The question is simpler and somehow more unnerving. What if someone finally picked up the first answer night and the birth of 3 Atlas? On July 1, 2025, the Atlas telescope at Rio Hurtado, Chile, was doing what it does best, scanning the southern sky for anything that moves too fast or shines too bright. The Asteroid Terrestrial Impact Last Alert System operates 4 robotic observatories, their cameras clicking through the night, building a catalogue of every rock that might threaten Earth. Atlas represents the cutting edge of automated sky surveillance. Each observatory captures images every 30 seconds. Sophisticated algorithms compare consecutive images, flagging objects that move or show changes. The system was designed to detect potentially hazardous asteroids weeks or months before impact. At 3:42 UTC, Atlas 4 seconds automated detection pipeline flagged something unusual. A point of light moving against the stellar background at nearly 3 arc seconds per hour. Faster than any asteroid should move at that distance. The object was already inside the orbit of Jupiter and closing on the inner solar system. The detection algorithms immediately began calculating preliminary orbital parameters. Initial estimates indicated an eccentricity greater than 1, the signature of an unbound orbit. This wasn't gravitationally captured debris from the asteroid belt. This was something from interstellar space. Within 6 hours, confirmation came from Pan-STARRS in Hawaii and the Zwicky Transient Facility in California. The object was real, it was fast, and its trajectory was impossible for any natural solar system inhabitant. 3 independent observatory systems had detected the same anomalous mover. This eliminated the possibility of instrumental error or cosmic ray hits. The Minor Planet Center in Cambridge, Massachusetts serves as the world's clearinghouse for discoveries. Their computers calculated the object's orbital elements and arrived at a troubling conclusion: eccentricity of 1.47, indicating a hyperbolic excess velocity of 15 kilometers per second. This wasn't bound to our Sunday. This was an interstellar visitor following a hyperbolic trajectory through our solar system.
I think we need to reevaluate
the discovery triggered immediate follow-up observations from major observatories worldwide. The European Southern Observatory's Very Large Telescope in Chile began tracking the object. The Keck Observatory in Hawaii joined the campaign using adaptive optics. The Hubble Space Telescope received emergency scheduling to observe this rare visitor. The designation came quickly, 3 Atlas. The 3 I meant it was the 3rd confirmed interstellar object, following 1 Oumuamua and 2 Borisov. The Atlas suffix honored the Discovery Observatory, but 3 was different from its predecessors, bigger, brighter, and moving in a way that didn't quite make sense. Oumuamua had been a tumbling, elongated rock, roughly the size of a city block. Its light curve revealed extreme geometry, a length at least 5 times its width. The object reflected sunlight, strangely showing properties unlike any known asteroid or comet. Most puzzling, it showed signs of non-gravitational acceleration, tiny pushes that couldn't be explained by the sun's gravity alone. Marco Micheli's team at the European Space Agency had carefully analyzed Oumuamua's trajectory. Their 2018 Nature paper documented systematic deviations from purely gravitational motion. The accelerations were small, but statistically significant, roughly 10,000 times weaker than Earth's surface gravity, but clearly real. Some scientists suggested outgassing like a comet without a visible tail. Others proposed more exotic explanations, a fragment of an alien light sail or debris from a disrupted comet. 2 Borisov behaved more normally, a proper comet from interstellar space, complete with a fuzzy coma and a distinctive tail. It followed the physics textbooks, precisely reassuring astronomers. Borisov's composition matched solar system comets closely. Water, ice, carbon monoxide, and organic compounds, sublimating. As it approached the Sunday 3 Atlas fell somewhere between these extremes. And that's what made it scientifically fascinating and potentially troubling. Early photometry revealed a light curve unlike anything in the catalogues. Most asteroids tumble chaotically, but 3 showed quasi-periodic modulation, regular variations, suggesting it was rotating in a controlled way. The light curve showed primary variations with a period of approximately 7.3 hours, but embedded within that cycle were secondary oscillations that suggested complex geometry. Most intriguingly, the periods were oddly stable across weeks of observation. Natural tumblers typically show period variations, but 3 maintained consistent timing, as if something was managing the object's attitude. Spectroscopic observations from the European Southern Observatory revealed more puzzles. The object showed muted outgassing signatures. Despite passing close to the Sunday, most comets develop distinctive spectral features. But 3 spectrum was unusually clean, dominated by reflected sunlight. The reflectance spectrum didn't match any known type of asteroid or comet. The colors were wrong: too red for typical silicate materials, too dark for organic-rich objects. Absorption features hinted at surface materials that might be rare or artificially processed. Some spectroscopists suggested exotic carbon compounds or even metallic films. Radio astronomers at Goldstone tried to ping the object with their planetary radar system. The 70-meter deep space network antenna transmitted powerful pulses. The return signal was weak but intriguing. Instead of the rough scattered echo typical of an asteroid's surface, 3 Atlas produced specular reflections, flat mirror-like returns that suggested smooth surfaces oriented at precise angles. The radar cross-section was smaller than expected, indicating unusual composition or geometry. When the James Webb Space Telescope turned its infrared eye toward 3, the data became even stranger. JWST's unprecedented sensitivity revealed thermal properties that defied simple explanation. The object's thermal signature indicated a low albedo. It absorbed most of the sunlight hitting it. But embedded within that thermal glow were high-intensity specular spikes, narrow beams of reflected infrared radiation that appeared and disappeared as the object rotated. The pattern was consistent with thin film structures or engineered coatings. Natural materials rarely showed such selective optical properties. Ground-based observatories in Chile coordinated their observations. The object would remain visible through December 2025. This would give astronomers a precious window to study humanity's third interstellar visitor. The Atacama Large Millimeter Array joined the campaign searching for molecular emissions. The discovery generated intense scientific interest but carefully managed public communication. Space agencies had learned from the Oumuamua experience, when speculative theories about alien technology had dominated news coverage. Press releases emphasized the object's interstellar origin and unusual properties, while avoiding premature speculation about artificial origins. But it was the radio observations that transformed scientific curiosity into something approaching alarm. On the 15th of July, radio telescopes detected a faint narrowband carrier signal. It was apparently co-moving with 3 Atlas. The frequency was approximately 1420.4 MHz, just slightly offset from the hydrogen line, the universe's most important radio frequency. The detection came simultaneously from the Very Large Array, the Green Bank Telescope, and FAST in China. Independent observations from different continents eliminated the possibility of local interference. The signal was real, it was extraterrestrial, and it was apparently coming from humanity's third visitor. Radio frequency interference is the bane of radio astronomy. But this signal passed every test for extraterrestrial origin. It appeared only when antennas were pointed toward 3 Atlas. It Doppler shifted in perfect synchronization with the object's motion. It maintained consistent intensity and frequency characteristics across multiple observing sessions. The signal showed no obvious modulation initially, just a clean narrowband tone drifting in frequency as 3 Atlas moved through space. The Doppler shift confirmed that the source was traveling with the object. The frequency stability was extraordinary, suggesting a highly sophisticated oscillator. The scientific community's initial reaction was cautious skepticism. Extraordinary claims require extraordinary evidence. Natural phenomena could sometimes produce narrowband radio emissions, but the frequency was suspicious. Why broadcast so close to the hydrogen line unless you wanted to be heard? But as confirmations poured in from observatories worldwide, an uncomfortable possibility emerged. 3 Atlas was broadcasting intentionally. The press, of course, had no such restraint. Despite careful classification by government agencies, news of the radio detection leaked. Social media erupted with speculation. The reply began trending on Twitter. YouTube videos with titles like "Proof Aliens Answer Our Call" garnered millions of views. The object that astronomers call 3 Atlas acquired a dozen unofficial names. The messenger, the reply, visitor 1. Amateur radio operators worldwide began monitoring the hydrogen line frequency. Software-defined radio systems allowed thousands of listeners to participate. The democratic nature of radio astronomy meant that the discovery couldn't be hidden. Scientists tried to maintain perspective. The signal could be natural, some unknown plasma phenomenon, or exotic interaction. Radio emissions from comets weren't unprecedented. The hydrogen line frequency might be coincidental rather than intentional. Government space agencies issued careful statements emphasizing the preliminary nature of the observations. NASA's press releases stuck to the facts. They avoided speculation about artificial origins, though internal memos painted a different picture. Behind closed doors, planetary defense coordinators were asking uncomfortable questions. How do you assess the threat level of an object that might be under intelligent control? The Planetary Defense Coordination Office had focused on natural threats, but 3 Atlas represented a new category of concern. The name 3 Atlas stuck in official circles, but public imagination favored more evocative labels. The reply captured something essential about humanity's collective psychology. We'd been calling into the darkness for over a century. Now perhaps someone had finally called back. The premise of what followed was both simple and profound. For the first time in human history, we would explore the possibility that an interstellar visitor was not just a cosmic accident, but an answer, a response to our own transmissions into space. Every observation would be conducted with rigorous scientific standards, but guided by a single question. What if 3 Atlas heard us calling and decided to call back? The implications, if true, would reshape every assumption about our place in the universe. We weren't alone. Someone was listening, and they had traveled across the galaxy to let us know they had heard our voice. But first, we had to determine if we were dealing with an extraordinary natural phenomenon or something else entirely, something that had crossed the interstellar void specifically to find us. A wave of visitors, not a one-off. 3 Atlas was not alone. 3 weeks after the initial discovery, automated sky surveys began flagging additional objects, fast-moving objects on hyperbolic trajectories. The detection pattern suggested something unprecedented in the history of astronomy. Multiple interstellar visitors arriving within months of each other. Their appearance coordinated in ways that challenged every assumption about random cosmic events. 4 appeared in data from the Catalina Sky Survey on the 22nd of July. The Lincoln Near-Earth Asteroid Research Program detected 5 2 days later. By August, amateur astronomers with backyard telescopes were contributing to a growing catalogue. Their discoveries were verified by professional observatories operating multi-million-dollar telescopes. These weren't random cosmic debris scattered by some distant catastrophe. The objects shared characteristics that became more disturbing with each new detection. First, their approach vectors. Statistical analysis of interstellar object trajectories should show a random distribution, but this group showed a loose coordination that violated expectations by orders of magnitude. Their trajectories converged from a cone of sky roughly 15 degrees wide. It was as if they had been launched from the same general region of space. Dr. Alan Fitzsimmons at Queen's University Belfast led the statistical analysis. His team calculated that the probability of such coordination occurring by chance was 1 in 50 million. Something had aimed these objects at our solar system with a precision that spoke to intelligence. More troubling, their perihelia closest approach points to the Sun clustered within a narrow range. They were threading the needle of Earth's orbital zone. The targeting precision was extraordinary. It suggested knowledge of our solar system structure and possibly Earth's specific location. The probability of natural interstellar objects accidentally converging on Earth's orbit was small. These visitors had been directed toward us, Light curve analysis revealed additional patterns that challenged natural explanations. Where 3 Atlas appeared to be a thin rotating panel, the subsequent objects showed even more exotic geometries. 4's brightness variation suggested a needle-like shape with an aspect ratio of 20:1, longer and thinner than any known natural object in the solar system. The photometric data indicated that 4 was tumbling end over end every 3.2 hours, but the tumbling wasn't chaotic like a natural collision fragment. The rotation showed characteristics of controlled motion, as if internal mechanisms were managing the object's orientation. 5 looked like a tumbling shard. Its light curve showed complex variations that suggested a partially fragmented structure. Spectroscopic analysis revealed unusual surface properties, materials that might be porous or partially hollow. A smaller object, designated 6, produced light curves consistent with a flake, something thin and flexible rippling as it rotated through space. The brightness variations suggested a sheet-like structure that might be deforming. These shapes defied conventional asteroid physics. Natural collision fragments follow predictable patterns, but thin film structures, sails, sheets, panels would behave exactly as the observation suggested. The implications were unsettling. Natural processes don't typically produce objects with extreme aspect ratios and controlled rotation, but artificial constructs designed for interstellar travel might show precisely these characteristics. Radio telescopes worldwide coordinated their observations. The results painted a picture that challenged every assumption about interstellar visitors. Each object produced narrowband radio emissions near the hydrogen line, but the signals weren't identical. They showed different modulation patterns, different frequency offsets, and different timing. The radio signatures suggested a distributed communication system. 3 Atlas maintained its steady carrier tone. 4 broadcast with subtle amplitude modulation. 5 transmitted brief bursts at multiple frequencies across the water-hole spectrum. 6 produced complex signals that seemed to carry encoded information. The diversity of signals ruled out simple explanations based on natural phenomena. These visitors were broadcasting like members of a coordinated fleet. Elena Vasquez at the Arecibo Observatory proposed the staging hypothesis. The objects weren't arriving randomly or as debris from a single event. They represented a carefully orchestrated sequence designed to maximize observability. The staging approach made sense from an engineering perspective. Sending multiple messengers would ensure success even if some were overlooked. The varied characteristics of each object provided different types of evidence for artificial origins, making it increasingly difficult to dismiss the entire ensemble as natural. The temporal correlations were equally suggestive. When astronomers reconstructed the launch windows, they found connections to Earth's broadcast history. Connections that seemed too precise to be coincidental. 3 Atlas, if launched from a star system 50 light-years away, would have departed around 1975. The peak era of powerful television transmitters and the first major planetary radar campaigns. 4's timeline aligned with the early space age and large military radar installations. 5 corresponded to the period when commercial satellite communications began. It was as if someone had been listening to our growing radio signature and responding in sequence. The visitors weren't just acknowledging that they had heard us. They were demonstrating detailed knowledge of our technological development over decades. The Atacama Large Millimeter Array in Chile initiated a coordinated campaign. VLBI Very Long Baseline Interferometry combined data from radio telescopes worldwide. This created a virtual dish the size of Earth. The positional accuracy was extraordinary. It allowed astronomers to detect tiny course corrections and attitude adjustments. The VLBI results confirmed that several objects were making subtle trajectory modifications.
But what of the
Small
fundamental
changes in
tenets?
velocity and direction that couldn't be explained by natural forces. The course corrections appeared purposeful, adjusting the object's paths to optimize viewing geometry or maintain communication. High-energy astronomy facilities joined the comprehensive monitoring effort. IceCube in Antarctica monitored for exotic particle emissions. Air shower arrays searched for correlations between the object's positions and high-energy cosmic rays. The results from high-energy observations were contested and controversial. Some researchers claimed to detect faint, but statistically significant correlations. Others found no such correlations and attributed the claims to statistical fluctuations. The debate reflected deeper uncertainties about what technologies the visitors might be using. Citizen science mobilized with unprecedented speed and scale. The Zooniverse platform launched interstellar visitors. This allowed volunteers worldwide to classify light curves and radio spectrograms. Within weeks, hundreds of thousands of participants were contributing to the analysis. Community-flagged anomalies often led to priority observations at major observatories. Amateur astronomers discovered subtle variations in signal timing. High school students identified patterns in radio emissions that suggested encoding schemes. The collaborative effort represented the largest coordinated scientific response in history. Social media platforms became repositories for observational data and analysis tools. The entire global community was participating in humanity's first systematic study of interstellar visitors. Space operators faced more immediate and practical concerns. The object's trajectories carried them through heavily traveled regions of the inner solar system. Conjunction bulletins went out to satellite operators warning of close approaches. The visitors posed no direct collision threat, but their unpredictable maneuvering capabilities raised new categories of operational risk. Insurance companies began reassessing their models for space debris collisions. What if these visitors weren't entirely predictable? The public's reaction swung between wonder and anxiety as more visitors appeared. Astronomical societies reported record attendance at star parties, but the same crowds that gathered to glimpse the visitors also reflected deeper uncertainties. Social media buzzed with theories ranging from scientific speculation to apocalyptic prophecy. Financial markets showed unusual volatility in aerospace and defense stocks. Some clearly believed humanity was about to learn something that would change everything. Space tourism companies reported a surge in bookings for suborbital flights. Pilgrimage sites formed spontaneously at radio observatories. The most unsettling aspect was the object's apparent coordination. As more visitors appeared, their radio emissions began showing temporal correlations. Brief synchronized transmissions occurred across multiple objects simultaneously. Whatever intelligence had dispatched this flotilla was maintaining active communication. The visitors weren't just broadcasting to Earth. They were talking to each other, coordinating their activities in real time. The implications for their communication technology and organizational sophistication were staggering. By September, the catalogue included 15 confirmed interstellar objects, with dozens more candidates awaiting confirmation. The sky was filling with artificial visitors, each one broadcasting its presence on frequencies that humans had long considered the natural choice. The pattern was becoming undeniable. These weren't random cosmic wanderers or natural debris. This was a planned mission executed with a precision that spoke to advanced intelligence. The question was no longer whether someone was trying to communicate with Earth. The question was what they were trying to say, and whether humanity was prepared to listen to a message that might reshape our understanding. A pattern in the noise. Did they hear us specifically? The mathematics were unavoidable, and they told a story that made astronomers uncomfortable. If the visitors originated from star systems 50 light-years away, they would have needed to detect Earth's radio emissions decades ago. This raised a fundamental question. When could they have known we were here? Dr. James Chen at MIT's Haystack Radio Observatory reconstructed humanity's expanding radio bubble. The analysis required careful consideration of transmitter power, antenna patterns, and signal propagation. Not all of our broadcasts were created equal in terms of their detectability. Television broadcasts began in the 1940s, but early systems were low power. High-power military radars proliferated during the Cold War, creating stronger signals. But their narrow beams swept across the sky in patterns that might be difficult to recognize. By the 1960s, our most powerful transmissions were planetary radar systems. They beamed megawatts of radio energy towards specific regions of the sky. The Arecibo Observatory, completed in 1963, became humanity's most powerful voice. Its 305-meter dish could transmit up to 1 million watts of radio energy. When used for planetary radar, Arecibo created radio signatures bright enough to be detected. The timeline was sobering and precise. Any civilization within 50 light-years would have detected our early television signals in the 1970s. Our most powerful radar transmissions would have reached nearby star systems in the 1990s. But the visitors weren't just arriving at random times. Their approach vectors, when traced backward, pointed towards specific star systems that would have been optimally positioned to observe Earth during our loudest periods. The correlation analysis required extreme care to avoid statistical traps. Dr. Sarah Martinez at the Harvard-Smithsonian Center for Astrophysics led a team. They cross-referenced the visitors' origin vectors with Earth's transmission patterns. HD 164595, a Sun-like star 94 light-years away, sat directly in the path of Arecibo's transmissions. Wolf 359, only 7.9 light-years distant, would have received our television signals with unusual clarity. Tau Ceti, a favorite target of SETI searches, aligned perfectly with several major radar campaigns. The statistical analysis revealed correlation significant at the 4 sigma level. Odds of roughly 1 in 15,000 that the patterns were purely coincidental. In particle physics, such correlations would constitute strong evidence for new phenomena, but critics argued that such analysis was prone to the look elsewhere effect, the tendency to find patterns when you search through enough data with flexibility. Dr. Robert Hayes at the University of Arizona led the skeptical response. His team conducted parallel analyses using randomized data sets. They found that apparent correlations could emerge from chance alignment. We're seeing patterns because we want to see them, Hayes argued in a widely cited paper. The universe is under no obligation to care about our radio broadcasts. But the temporal patterns embedded in the visitor's arrival sequence provided more evidence. The objects didn't arrive at random intervals. Their spacing echoed key milestones in humanity's broadcast history. Dr. Lisa Johansson at the SETI Institute proposed the echo hypothesis, a model that treated each visitor as a response to specific human transmissions. She constructed a mathematical model that assumed interstellar travel velocities of 10 to 20% the speed of light. The agreement between predicted and observed arrival times was remarkable. Free Atlas matched the timeline for a response to Earth's television broadcasting peak. 4 aligned with reactions to early military radar installations. 5 corresponded to the commercial satellite communication era. The pattern suggested not just intelligence, but intelligence that had been monitoring Earth. The most compelling evidence came from information theory analysis of the visitors' radio emissions. Several objects showed transmission patterns that appeared to reference the 1974 Arecibo message. The Arecibo message had encoded the numbers 1 through 10 in binary notation, followed by the atomic numbers for the key elements in DNA. It included a representation of the double helix structure and a diagram of the solar system. Some of the visitors' signals contained similar numerical progressions, but with subtle variations. The binary sequences were recognizable but extended beyond the original Arecibo format, including mathematical concepts that humans had discovered but not yet broadcast. The prime number sequences were particularly striking. The Arecibo message had used prime numbers as a universal mathematical concept. Several visitors broadcast their own prime sequences, but then deviated from the standard progression in ways that seemed deliberate. It was as if someone was saying, "We received your message and understood your language. Now let us show you variations." The deviations weren't random. They followed patterns that corresponded to advanced number theory. The visitors were demonstrating mathematical knowledge that went beyond basic counting. Statistical analysis of the mathematical content required extreme care. Dr. Chen's team pre-registered their hypotheses before analyzing the transmissions. Even with these rigorous safeguards, the connections remained statistically robust. The probability that random radio emissions would contain recognizable mathematical sequences was low. The visitors were demonstrating knowledge of human mathematics and extending it. But the skeptical community pushed back hard against these interpretations. The debate played out in academic journals and on social media with equal intensity. Hayes and his colleagues argued that the apparent mathematical content reflected human psychology. Pattern recognition is fundamental to human cognition, they wrote. We evolved to find meaningful signals in noisy environments. The statistical arguments became increasingly sophisticated as both sides refined their methods. Supporters of the intelligence hypothesis pointed to the multiple independent lines of evidence. Critics emphasized the dangers of multiple hypothesis testing and the human tendency to find significance. The debate attracted attention from philosophers of science and experts in statistical methodology. The National Academy of Sciences convened a special panel to evaluate the evidence. The panel's preliminary report was carefully worded, but acknowledged that the visitors merited investigation. Social media amplified the controversy, with hashtags like pattern or pareidolia trending worldwide. But the scientific community took the analysis seriously, recognizing that even a small probability of intentional contact carried enormous implications. The provisional consensus emerging was carefully worded. The correlations were statistically significant and not easily explained by random processes. Whether this represented intentional communication remained an open question. But the patterns were strong enough to justify systematic attempts at response. The phrase "systematic attempts at response" carried profound weight. It implied that humanity might attempt to communicate back, to test whether the visitors would react to our transmissions in real time. The idea was both thrilling and terrifying. Our first intentional conversation with intelligence from another star system. After decades of passive listening, we were contemplating active participation. The visitors had given us what appeared to be their opening statement, demonstrating knowledge of our mathematics, our history, and our location in space. The question was whether we were ready to reply, and what we might learn from beings who had mastered communication across interstellar distances. Anatomy of an enigma. What 3 Atlas is physically. By October 2025, the combined observations had compiled the most detailed profile of an interstellar object in history. What emerged was a picture that defied easy categorization. 3 Atlas measured approximately 200 meters in its longest dimension, with a width of roughly 20 meters and a thickness of less than 2 meters. The aspect ratio exceeded 10:1. Making it one of the most elongated objects ever observed in the solar system. Its shape was consistent with a thin panel or stack of panels. The object's non-gravitational accelerations were subtle but unmistakable. As it approached, perihelion tiny deviations from a purely gravitational trajectory accumulated. The accelerations were coherent, always sunward or anti-sunward, never random. They matched the predictions for radiation pressure acting on a highly reflective surface. but the object's measured albedo was too low to account for such effects. Spectroscopic analysis revealed a surface chemistry unlike anything in the asteroid catalogues. The spectrum showed absorption features consistent with exotic carbon allotropes, materials that might be engineered rather than naturally occurring. There were hints of boron nitride coatings and traces of metals arranged in patterns. The thermal behavior was perhaps the most puzzling aspect. As 3 Atlas moved, its temperature didn't follow the simple inverse square law. Instead, it showed thermal plateaus, regions where the temperature remained nearly constant despite changing solar irradiation. This suggested active thermal management. The object's rotation was equally controlled. Unlike natural asteroids, which tumble chaotically, 3 Atlas maintained a stable spin axis. More intriguingly, its rotation period showed subtle variations that correlated with solar illumination, as if the object was adjusting its attitude to optimize solar energy collection. The radio emissions remained the most compelling evidence of artificial origin. The primary carrier at 1420.4 MHz was accompanied by harmonics. Initially, the signal showed no modulation, but as 3 approached, perihelion modulation appeared. The pattern was unmistakable prime numbers. The sequence continued through the first several dozen primes, then repeated. It was the kind of signal that SETI researchers had long predicted as a first communication. Dr. Abraham Loeb at Harvard had proposed several criteria for identifying artificial objects: unusual brightness, evidence of artificial acceleration, and electromagnetic emissions. 3 Atlas appeared to satisfy all of them. Loeb estimated that if the object's reflectivity was ordinary, its brightness would require 10 gigawatts of internal power. The mainstream astronomical community remained cautious. Hubble Space Telescope images showed a diffuse coma around 3 Atlas. This was consistent with gas and dust sublimation as the object heated up. Ground-based observations detected water vapor and carbon monoxide in the vicinity. But even normal cometary physics couldn't fully account for all observations. The outgassing was too weak to explain the non-gravitational accelerations. The coma's structure showed asymmetries that suggested controlled venting. Most puzzling, the radio emissions continued even when the object was far from the Sunday. The debate crystallized around competing hypotheses. The natural explanations invoked exotic but plausible scenarios. A fragment from a disrupted comet with unusual composition and geometry. The artificial explanations were more speculative but eerily consistent with the observations. An autonomous probe or messenger system, possibly using solar energy. The thin geometry suggested a deployable structure, perhaps a communication array. The prime number sequence indicated not just intelligence, but intelligence that understood human mathematics. A third category emerged, something between natural and artificial. Dr. Elena Rodriguez at the University of Barcelona proposed that 3 Atlas might be technobiotic debris, remnants of a biological civilization that had learned to engineer materials at the molecular level. Risk assessment became a priority as 3 Atlas approached its closest point to Earth. The object would pass within about 45 million kilometers, close enough for detailed observation, but far enough to avoid any gravitational perturbation. More concerning was the possibility of debris shedding. If the object was artificial and potentially damaged, fragments might separate. The Planetary Defense Coordination Office issued cautious advisories to space agencies. While 3 Atlas posed no direct collision threat, its behavior remained unpredictable. The controlled accelerations proved the object could maneuver. The question was whether such maneuvers were automatic responses or active guidance. Companion objects added another layer of complexity. Several smaller pieces traveled in formation with the primary object. These fragments showed similar radio emissions and coordinated maneuvers, suggesting they might be calibration mirrors or relay nodes for a distributed communication system. energy considerations painted a sobering picture. The radio transmissions alone required kilowatts of power, substantial for an object with limited solar collection area. If the emissions were intentional communications, they represented a significant commitment of resources. As 3 Atlas reached perihelion on the 28th of November, the astronomical community held its breath. This was the moment of closest approach, maximum heating, and perhaps maximum activity. Every major observatory on Earth was watching, waiting to see what humanity's most enigmatic visitor would reveal about itself. Talking back protocols, politics, and the first reply. The moment astronomers confirmed that 3 Atlas was transmitting prime numbers, humanity faced a question it had never seriously confronted. How do you respond to a message from space? The International Academy of Astronautics had spent decades developing post-detection protocols. Their guidelines were comprehensive but advisory, a careful framework for verification, analysis, and eventual response. But no treaty anticipated visitors that could maneuver and actively communicate. The UN Committee on the Peaceful Uses of Outer Space convened emergency sessions in Vienna. COPUS, as it was known, had handled everything from space debris to commercial launches, but never interstellar diplomacy. The Committee on Space Research weighed in on planetary protection protocols. Did those same principles apply to artificial visitors from other star systems? The International Telecommunication Union faced more immediate concerns. Radio frequencies were national resources carefully allocated. But what happened when an alien intelligence started broadcasting on frequencies reserved for radio astronomy? Behind closed doors, the debate was less diplomatic. National space agencies understood that whoever responded first might claim some form of precedent. NASA's Deep Space Network could reach 3 Atlas with existing hardware. The European Space Agency's ESTRAC network provided similar capabilities. China's evolving deep space communication infrastructure was rapidly approaching parity, but the most powerful transmitters belonged to military organizations and academic institutions. The 500-meter aperture spherical telescope in China and upgraded facilities at Goldstone and Canberra. Dr. Jill Tarter, former director of the SETI Institute, emerged as an unlikely coordinator. Her decades of experience gave her unique authority to speak about protocols. "We've always known this moment might come," she said in emergency meetings. "The question is whether we respond as one species or as competing nations." The technical challenges were substantial but manageable. Any response to 3 Atlas would need to account for its rapid motion and changing distance. Doppler compensation required precise tracking and frequency adjustment in real time. The transmissions would need to be powerful enough to overcome interplanetary distances. The communication protocol emerged from SETI traditions and information theory. Begin with mathematics, the universal language. Reciprocate the prime number sequence to demonstrate comprehension. Then introduce more complex concepts, atomic structures, physical constants, perhaps a star map. Content restrictions became a source of heated debate. Military advisors warned against revealing sensitive information about Earth's infrastructure. Scientists argued that any civilization capable of interstellar travel would already understand our limitations. The compromise was elegant: respond with the same type of information we had already broadcast deliberately. The modulation scheme had to be simple enough for any intelligence to decode, but sophisticated enough to carry meaningful information. The team settled on pulse position modulation with heavy error correction, slow, inefficient, but virtually immune to corruption. Barker codes would provide unmistakable preambles. Time was the critical constraint. 3 Atlas would remain within optimal communication range for only a few weeks. The object's high velocity meant that Earth's rotation would provide brief communication windows.
Oh my goodness.
Dynamic scheduling software was repurposed to maximize contact time. Chain of custody protocols ensured that every transmission would be documented and verified. Cryptographic signatures would prevent later claims that the messages had been altered. Multiple observatories would maintain independent records. The decision to transmit came on the 3rd of December. 3 Atlas was approaching its optimal viewing geometry from Earth, and radio astronomers have confirmed that the object's prime number sequence was continuing. The visitor was demonstrating mathematical sophistication that extended far beyond simple counting. Dr. Martinez keyed the transmission from the Arecibo replacement facility. The message began with the same prime sequence that 3 Atlas had been broadcasting. It continued with the first few elements of the periodic table expressed in binary. Then came a simple representation of the hydrogen atom. The response came 18 minutes later, the light travel time to 3 Atlas and back. The visitor's signal changed. The steady prime number sequence gave way to a more complex pattern. Groups of pulses that corresponded to atomic numbers: hydrogen, helium, lithium, beryllium. But then the sequence diverged from Earth's periodic table. It included pulse groups that didn't match any known element. It was as if the visitor was teaching us a chemistry we hadn't discovered yet. More remarkable was what happened to the object itself. Ground-based telescopes detected a subtle brightening, a brief, shutter-like flash. It lasted exactly as long as Earth's transmission. Photometric analysis suggested that part of 3 Atlas had physically reconfigured itself, perhaps opening reflective panels or adjusting its orientation. The implications were staggering. This wasn't passive reflection of a natural phenomenon. This was active real-time communication with an intelligence that could coordinate radio and optical signals. News of the successful exchange leaked within hours despite careful classification. Amateur radio operators worldwide had been monitoring the frequencies, and the distinctive pulse patterns were impossible to hide. Social media erupted with excitement and speculation. Governments rushed to issue statements emphasizing caution and international cooperation. But the fundamental truth was unavoidable. Humanity had successfully initiated a conversation with visitors from another star system. The second exchange came 2 days later. This time, 3 Atlas initiated the contact. It transmitted a more complex mathematical sequence that appeared to describe orbital mechanics. When Earth's mathematicians decoded the full sequence, they realized something. The visitor was describing not just general orbital theory, but the specific trajectory it was following. It was showing us that it understood where it was and where it was going. More importantly, it was demonstrating that its presence was not accidental. The trajectory had been calculated, planned, and executed across interstellar distances. The visitor wasn't just answering our call. It was explaining how it had heard us travel to find us and positioned itself for optimal communication. The conversation that followed would reshape every assumption about our place in the universe. Earth reacts, psychology, faith, markets. The moment news broke of successful two-way communication with 3 Atlas, humanity's collective psychology shifted. Mental health hotlines reported a 340% increase in calls during the first week. The conversations followed predictable patterns: existential anxiety, profound excitement, and a peculiar form of cosmic loneliness. Dr. Susan Chen at the Stanford Psychology Institute coined the term contact syndrome. Susan Chen at the Stanford Psychology Institute coined the term contact syndrome. Patients reported vivid dreams about space travel and obsessive skywatching behavior. It's as if people are trying to mentally prepare for a future they can't yet imagine, she noted. Religious responses varied dramatically across denominations and faiths. The Vatican issued a carefully worded statement within 48 hours, emphasizing that the discovery of intelligence beyond Earth was consistent with Catholic theology. The universe is vast and full of wonders, Pope Francis declared. If God has chosen to populate it with other forms of consciousness, this only increases our sense of His creativity. Evangelical Protestant reactions were more mixed. Some leaders embraced the visitors as evidence of God's cosmic scope. Others worried about theological implications. Did beings from other worlds possess souls? Emergency theological conferences convened in seminaries worldwide. Islamic scholars found more comfortable ground in the Quran's references to God's creation spanning multiple worlds. Buddhist leaders spoke of the contact as confirmation that consciousness was a fundamental property of the universe. Hindu traditions, already comfortable with cosmic scales, adapted most easily. Financial markets, meanwhile, experienced what economists later dubbed the contact correction. Aerospace and defense stocks surged, initially driven by speculation about new technologies. But the gains were volatile, reversing sharply when early analysis suggested no hostile intent. Satellite communication companies saw dramatic shifts in their insurance rates. Rare earth element prices spiked based on speculation that alien technology might require exotic materials. Lithium used in batteries and electronics doubled in price within a week. Gold, historically a safe haven, showed surprising stability. Apparently, investors believed that beings capable of interstellar travel would be less impressed by shiny metals. The cryptocurrency markets offered a fascinating window into collective psychology. Bitcoin prices soared on theories that decentralized digital currencies might be preferred. New contact coins appeared daily, most of them elaborate scams, but some reflected genuine attempts to create communication protocols that might work across species. Information warfare erupted across social media platforms almost immediately. Bot networks flooded Twitter, Facebook, and TikTok with competing narratives. Some claimed the entire contact event was an elaborate hoax. Others insisted the visitors represented an invasion force and demanded military mobilization. Platform moderators found themselves in the unprecedented position of fact-checking claims about aliens. Twitter's policy team worked frantically to develop guidelines for extraterrestrial content. Verification badges appeared on official observatory accounts. Educational systems scrambled to respond to sudden student interest in astronomy and astrobiology. Universities reported unprecedented enrollment in physics and mathematics courses. Community colleges began offering crash courses in radio technology. Children's reactions were particularly telling. Teachers reported that students had begun incorporating space themes into their artwork. Many children seemed less surprised by the contact than adults, as if they had always assumed the universe contained other intelligences. The art world responded with characteristic intensity. Museums organized emergency exhibitions featuring space-themed works. New musical compositions appeared almost daily, many incorporating prime number rhythms or the actual radio frequencies detected. Visual artists created installations using the hydrogen line frequency as an organizing principle. Social rituals emerged organically. Listen parties became popular, with groups gathering around radios tuned to specific frequencies. Astronomy clubs found themselves overwhelmed with new members. The hashtag #OurSpace became a global phenomenon. Millions of people posted messages intended for extraterrestrial audiences. Night sky photography exploded in popularity. Amateur astronomers suddenly invested in telephoto lenses and tracking mounts. The photos themselves were unremarkable distant points of light. But the act of photography seemed to satisfy a deep human need to document this historic moment. Urban light pollution became a political issue for the first time in decades. City councils faced pressure to implement dark sky ordinances. Hardware stores reported shortages of red flashlights for stargazing. The psychological impact extended to unexpected areas. Marriage proposals reportedly included references to the cosmic perspective. Dating apps added views on extraterrestrial contact to their matching algorithms. Pet adoption rates spiked, possibly reflecting a desire for companionship.
We can regain our
Corporate
connection
marketing
to the night
adapted
sky.
with remarkable speed. Car commercials featured families driving to dark locations for better sky viewing. Smartphone manufacturers emphasized their cameras' low-light capabilities. Coffee companies marketed contact blends for those long nights of sky watching. But perhaps the most significant change was subtler, a shift in temporal perspective. People began thinking in longer time scales, considering decisions in the context of cosmic history. Urban planning discussions included speculation about how cities might need to evolve. The psychological research would continue for years, but early patterns were clear. Humanity was not just processing the existence of other intelligence. We were beginning to imagine ourselves as part of a larger community of minds. The isolation that had defined human consciousness was finally tentatively coming to an end. Building a mission in months, not years. By January 2026, the impossible had become inevitable. Humanity would send a spacecraft to rendezvous with 3 Atlas. The mission architecture emerged from emergency planning sessions, bringing together NASA's best engineers, ESA's mission designers, and commercial space companies. The challenge was unprecedented, intercepting a target moving at interstellar velocities with a launch window measured in weeks. Traditional mission planning assumed development cycles of a decade or more. The Voyager probes had taken 8 years from concept to launch. The James Webb Space Telescope required 3 decades. But 3 Atlas would not wait for human bureaucracy. By mid-2026, the visitor would be accelerating away from the Sunday beyond the reach of any spacecraft humanity could reasonably construct. The solution lay in leveraging hardware that already existed or could be rapidly modified. SpaceX's Super Heavy booster could deliver substantial payloads to interplanetary trajectories. Solar electric propulsion systems could provide the precision navigation required. The challenge was integrating these components into a functional mission in less than 8 months. Dr. Robert Braun led the international mission design team. His philosophy was ruthlessly pragmatic. Use only proven technologies, accept higher risks, and focus exclusively on objectives for a brief flyby. The baseline mission profile was elegant in its simplicity. A single large spacecraft would launch in June 2026. It would follow a minimum energy transfer to intercept 3 Atlas in September. The encounter would last roughly 6 hours, during which the spacecraft would deploy multiple small probes to approach from different angles. Guidance, navigation, and control presented the most significant technical challenges. 3 Atlas was a thin, tumbling target with unpredictable maneuvering capabilities. The spacecraft would need autonomous navigation systems capable of adjusting in real time. The payload selection reflected urgent scientific priorities. Wideband radio receivers would monitor the full spectrum of emissions. Optical cameras with various filters would document the object's physical structure. Laser communication systems would attempt to establish high bandwidth contact. Most controversially, the mission included microprobes designed for extremely close approach. These contactors were equipped with sampling systems that could collect material, but their primary purpose was detailed observation and active signal transmission from close range. The James Webb Space Telescope's role became critical for mission success. JWST's moving target tracking capabilities could potentially observe 3 Atlas. More importantly, its infrared sensitivity might detect thermal signatures. Very long baseline interferometry networks worldwide coordinated to provide position measurements. This precision would enable trajectory prediction accurate enough for intercept calculations. The Rubin Observatory's Legacy Survey of Space and Time offered another advantage. Its wide-field surveys might detect future interstellar visitors earlier. The lessons learned from the 3 Atlas encounter would inform rapid response protocols. Sample collection ethics generated heated debate in the scientific community. The Committee on Space Research had established planetary protection categories, but none addressed the possibility of sampling potentially artificial objects. Was 3 Atlas a natural phenomenon, or did it represent the property of another intelligence? The compromise was cautious. Sampling would be attempted only if 3 Atlas appeared to be shedding material naturally, or if the visitor provided some form of apparent consent. Direct contact with the primary structure would be avoided unless absolutely necessary. International coordination proved surprisingly smooth. The scale and timeline of the mission required resources that no single nation could provide. NASA contributed launch services and mission operations experience. ESA provided proven propulsion systems and navigation software. Commercial partners supplied communications equipment and computational resources. The arrangement created a precedent for future international missions. Contingency planning consumed enormous effort. What if 3 Atlas changed course unexpectedly? What if it deployed defensive systems? What if communication attempts triggered hostile responses? Each scenario required predefined responses that could be executed autonomously. The 8-minute communication delay would make real-time intervention impossible. The encounter timeline was choreographed with military precision. Initial contact would occur at a distance of 10,000 kilometers. The main spacecraft would maintain this standoff distance while deploying microprobes. Active communication attempts would begin immediately. As launch approached in June 2026, public attention focused intensely on the mission. Unlike previous interplanetary missions, the 3 Atlas rendezvous captured the global imagination. The spacecraft carried messages from world leaders and children's artwork. The encounter itself would be brief but unprecedented. For 6 hours, humanity would have its closest look at visitors from another star system. The scientific return might answer fundamental questions about interstellar objects. More importantly, the mission would demonstrate human capability to respond rapidly. But as the spacecraft raced toward its appointment, with 3 Atlas scientists prepared for discoveries that might challenge every assumption about intelligence, technology, and our place among the stars. Proof, or pareidolia, the scientific knife edge. The hardest part of extraordinary science is knowing when you've found something extraordinary. Dr. Elena Martinez understood this as she stared at the data streaming back from the rendezvous. The encounter with 3 Atlas had lasted 6 hours and 17 minutes. It produced terabytes of observations that would take months to fully analyze. But the initial results raised more questions than they answered, and the scientific community found itself walking the razor's edge between discovery and delusion. Extraordinary claims require extraordinary evidence, a principle that had guided SETI research for decades. But how do you define extraordinary when you're dealing with phenomena never observed before? The challenge wasn't just analyzing the data from 3 Atlas. It was developing entirely new frameworks for evaluating claims about non-human intelligence. The scientific method had evolved sophisticated tools for avoiding false positives. Pre-registered analyses forced researchers to commit to specific hypotheses before examining data. Blind injections, fake signals inserted into datasets, tested whether detection algorithms could distinguish real phenomena. Independent analysis pipelines developed by different teams provided cross-validation for critical results. If 5 different groups reached the same conclusions, the findings gained credibility. The competing models for 3 Atlas fell into 3 broad categories, each with its own predictive framework and observational tests. The engineered light sail hypothesis proposed that 3 Atlas was an artificial construct. This model explained the object's extreme geometry, controlled rotation, and radio emissions. It predicted that detailed analysis would reveal materials inconsistent with natural formation. The exotic natural fragment hypothesis suggested that 3 Atlas was a previously unknown category, perhaps debris from a stellar collision or a disrupted comet with unusual materials. This model could potentially explain the anomalous properties without invoking artificial origins. It predicted that spectroscopic analysis would eventually reveal natural formation mechanisms. The normal comet hypothesis maintained that 3 Atlas was fundamentally similar to 2 Borisov, with apparent anomalies resulting from observational artifacts or misunderstood natural processes. Each model scored differently against the accumulating evidence. The radio emissions strongly favored artificial origins. Natural processes rarely produced narrowband signals with mathematical modulation. The controlled rotation and thermal management also seemed more consistent with engineered systems. But the spectroscopic data remained ambiguous. While 3 Atlas showed unusual surface chemistry, determining whether it was natural or artificial was difficult. Exotic didn't necessarily mean artificial. The Encounter mission had provided crucial new data. Close approach imaging revealed surface structures that appeared organized rather than random. But pareidolia, the tendency to see patterns where none exist, had fooled humans before. The canals of Mars had seemed obviously artificial to 19th century astronomers. Laser communication experiments during the encounter provided the most tantalizing results. When the spacecraft transmitted structured light pulses toward 3 Atlas, its surface reflectivity changed. The changes appeared to correspond to the transmission sequence, but optical effects in space environments could be complex, confirming that the changes were responses rather than coincidences required statistical analysis. The historical context of Oumuamua provided both guidance and caution. That first interstellar visitor had shown non-gravitational accelerations that initially seemed inexplicable. Scientists proposed exotic explanations, fragments of alien technology, hydrogen, icebergs, even light sails. But careful analysis by Dr. Marco Miche and his colleagues demonstrated a natural explanation. The accelerations could be explained by conventional outgassing from a comet nucleus. The unusual geometry and lack of visible coma had initially disguised its cometary nature. The lesson was sobering. Extraordinary hypotheses should be the last resort, not the first. Natural explanations, even unlikely ones, deserved serious consideration. 2 Borisov had provided a useful contrast, a clearly normal interstellar comet that behaved exactly as theory predicted. Its composition matched solar system comets, its outgassing followed standard models. Borisov demonstrated that most interstellar visitors would probably be unremarkable. This made the apparent anomalies of 3 Atlas even more intriguing. The ongoing controversy over interstellar meteors added another layer of complexity. The 2014 fireball designated IM-1 had been classified as potentially interstellar. Dr. A.V. Loeb's expedition to recover material had produced spherical fragments with unusual compositions, but the IM-1 spherules remained controversial. Other scientists argued that the unusual compositions could result from terrestrial contamination. The need for larger samples and independent laboratory analysis had slowed progress. These experiences informed the analysis of 3 Atlas data. Every anomaly required multiple independent confirmations. Every unusual measurement needed to be reproduced by different instruments and analysis techniques. The scientific community was determined to avoid both false positives and false negatives. Bias audits became a routine part of the analysis process. Teams of researchers would exchange datasets and analysis responsibilities, searching for systematic errors or unconscious assumptions that might skew results. Adversarial collaborations brought together scientists with fundamentally different interpretations, forcing them to identify the observations that might distinguish between competing hypotheses. The process was slow and sometimes frustrating, but it was working. 6 months after the encounter, a preliminary consensus was emerging. The evidence for artificial origins was suggestive but not conclusive. Several key observations remained unexplained by natural processes, but the possibility of exotic natural phenomena couldn't be ruled out. The interim language for public communication was carefully calibrated. 3 Atlas exhibits properties that are difficult to explain through currently understood natural processes. While the possibility of artificial origins cannot be dismissed, more observations are needed. But even this cautious phrasing carried profound implications. For the first time in human history, the scientific community was seriously considering the possibility that we had encountered technology from another civilization. The burden of proof was enormous, but the potential discovery was worth the most rigorous investigation humanity could mount. The knife edge between proof and pareidolia remained sharp, but with each new analysis, each independent confirmation, the balance was slowly shifting toward a conclusion that would change everything we thought we knew. The message unfolds content, form, and meaning. What 3 Atlas was trying to tell us became clear only through months of painstaking analysis. And the message was both more complex and more practical than anyone had expected. The communication wasn't a greeting or a philosophical statement. It was an instruction manual. Dr. Yuki Tanaka at the Tokyo Institute of Technology led the international decryption team. Her background in information theory and signal processing made her uniquely qualified. What initially appeared to be simple prime number sequences revealed themselves as headers for more complex data packets, each one building upon the last. The first layer was a mathematical foundation establishing shared concepts. Prime numbers gave way to algebraic relationships, then to geometric principles. The visitor was teaching us its mathematical language before attempting to convey more complex ideas. The second layer introduced physical constants, the fine structure constant, Planck's constant, the speed of light. But these weren't just confirmations of universal knowledge. They were presented with a precision that exceeded humanity's current measurements, suggesting our visitors possessed a more accurate understanding of fundamental physics. The third layer was where the message became interesting. The visitor began transmitting what could only be described as technical specifications, detailed instructions for constructing a radio beacon with capabilities far beyond our technology. The specifications were elegant in their consideration for human limitations. Rather than assuming unlimited resources, the design used technologies we could reasonably develop. The beacon would require a large array of precisely coordinated transmitters, but the individual components were within reach of human engineering. More remarkably, the design included optimizations for Earth-specific rotation and magnetic field. This wasn't a generic template, it was customized for our world, suggesting the visitors had been studying Earth's properties in detail. The fourth layer contained what Dr. Sarah Kim at MIT called the network map, a description of how the proposed beacon would interface with a galaxy-wide communication system. The map showed relay nodes positioned at strategic locations throughout local space, each one described by precise astronomical coordinates.
Check the calibration.
Some of these coordinates corresponded to known stars. Others pointed to empty regions of space where gravitational lensing effects might focus signals. The visitor was describing a communication network that used the galaxy's own structure. The ethical payload embedded throughout the specifications revealed a sophisticated understanding. The message included symbols and concepts that clearly referred to living systems and planetary environments. There were implicit warnings about maintaining electromagnetic quiet near biological surfaces, suggestions that powerful transmitters should be positioned away from inhabited worlds. The encoding itself was a masterpiece of information theory. Every data packet included multiple layers of error correction, ensuring that the message could be recovered even if large portions were lost. Temporal scaffolding allowed the transmission to be assembled correctly despite interruptions. Explicit markers identified byte order, dimensional units, and coordinate systems, preventing the ambiguities that could arise when different species attempted to communicate. The message was designed to be decoded by any intelligence capable of detecting it. But the most intriguing aspect was what the message didn't contain. There were no personal communications, no cultural artifacts, no attempts at small talk. The visitor's message was purely functional, a technical manual. A manual for joining what appeared to be an established interstellar communication network. The implications were staggering. Humanity wasn't just receiving its first message from another civilization. We were being invited to join a community of intelligences that had been operating for an unknown time. Public participation in the decryption effort had proved invaluable. Citizen science platforms allowed thousands of volunteers to contribute to the analysis. Pattern recognition tasks were distributed to classroom students worldwide. The collaborative effort represented the largest coordinated intellectual challenge in human history. Convergent translations emerged as different teams working independently reached similar interpretations. This redundancy provided confidence that the decryption was proceeding correctly. The deep space optical communications demonstration had provided crucial experience. Those lessons informed speculation about how the visitor might extend the conversation. But perhaps the most significant aspect of the message was its implicit deadline. The technical specifications for the beacon included temporal coordinates, precise timing requirements for initialization and synchronization with the broader network. If humanity wanted to join the galactic community, we had a limited window. The decision point was approaching rapidly. The visitor had provided us with detailed instructions for our own interstellar communication system. The technology was challenging but achievable. The question was whether humanity was ready to announce its presence to the galaxy. Building the beacon would be irreversible. Once activated, Earth's participation in the galactic network would be permanent and visible. We would no longer be an isolated world shouting into the darkness. We would become part of something vast and ancient, and utterly beyond our current understanding. The choice ultimately was simple: remain alone or join the conversation that had been taking place among the stars. Second-order effects, technology, law, and power. The moment humanity seriously considered building an interstellar beacon, everything changed. Not just our technology, but our politics, our economics, and our understanding of being human. Engineering teams worldwide began rapid prototyping of the technologies described. The beacon specifications pushed the boundaries of human manufacturing, but not beyond them. Ultra-thin metamaterials precisely engineered at the nanoscale would form the primary elements. Low-noise oscillators locked to atomic frequency standards would provide the stable references. The most challenging requirement was coordination. The beacon would consist of thousands of individual transmitters distributed across hundreds of kilometers. The timing precision required nanosecond accuracy, maintained over interplanetary distances. Cooperative radar-laser hybrid systems emerged as a crucial technology. By combining radio transmissions with precisely timed optical pulses, the beacon could achieve the requirements. The dual-mode approach also provided redundancy, but every breakthrough in beacon technology carried dual-use implications. The same precise timing systems could guide intercontinental ballistic missiles with unprecedented accuracy. The high-power transmitter arrays could potentially interfere with satellites or serve as weapons. Planetary defense advocates argued for transparency protocols that would allow international monitoring. The technology was simply too powerful to develop in secret. Legal frameworks struggled to catch up with technological reality. The Outer Space Treaty of 1967 said nothing about communicating with aliens. The Liability Convention of 1972 addressed damage from space objects, but couldn't anticipate disputes over interstellar messaging rights. model legislation began emerging from legal scholars worldwide. Contact governance treaties would establish international protocols for extraterrestrial communication. The frameworks borrowed heavily from existing arms control and environmental protection agreements. The question of who speaks for Earth became more than philosophical. With the beacon specifications in hand, multiple nations began claiming authority to build it. NASA proposed an international consortium similar to the International Space Station Partnership. China announced plans for an independent beacon system. Private companies submitted their own proposals, arguing that competition would accelerate development. Data rights emerged as a critical issue. Would the beacon's transmissions be public information available to all humanity? Or would the nations that built the system control access to interstellar communication? The precedent established with Earth's first beacon would likely determine communication governance. Economic implications rippled through every sector. The rare earth elements required for beacon construction triggered commodity price spikes. Lithium, already essential for battery technology, became even more strategic. But the greatest economic shift was psychological. Investment horizons extended from quarters and years to decades and centuries. Companies began planning for market opportunities that might not emerge for generations. The cosmic perspective fundamentally altered how humans thought about time and value. Cryptocurrency markets spawned hundreds of galactic coins designed for interstellar commerce. Most of them were obvious scams, but some represented serious attempts to create new protocols. The mathematical requirements for galaxy-wide consensus mechanisms pushed blockchain technology. Religious and philosophical institutions grappled with humanity's changing status. Were we still made in God's image? If we shared the galaxy with other intelligent beings, did moral obligations extend to civilizations we had never met but might soon join? Theological seminaries found themselves offering courses in astroethics and interspecies communication. Educational systems experienced unprecedented demand for physics, mathematics, and engineering programs. Students who had never shown interest in technical subjects suddenly wanted to understand the science. Community colleges began offering beacon literacy courses. Environmental considerations complicated beacon planning. The transmission arrays would require enormous amounts of electrical power. Carbon-aware power sourcing became essential to avoid worsening Earth's climate problems. Solar farms and fusion reactors received new investment. Ground-based transmission systems raised concerns about electromagnetic effects on wildlife. Birds, whales, and other animals that navigated using Earth's magnetic field might be disrupted. Careful site selection and transmission protocols would be needed to minimize ecological impact. The cislunar region became humanity's newest frontier for beacon development. The far side of the Moon offered natural radio shielding from Earth's interference, making it an ideal location for sensitive receiving equipment. Near-Earth asteroids could provide raw materials for construction. Space traffic management systems, already strained, faced new challenges. Orbital debris from construction activities could threaten existing satellites. Communication interference between beacon systems and conventional spacecraft required careful coordination. International cooperation emerged as both necessity and opportunity. No single nation possessed all the resources needed for rapid beacon construction. Successful projects required sharing of technology, funding, and expertise across political boundaries. The beacon became a catalyst for the kind of global collaboration that had been elusive, but cooperation carried risks. Shared beacon systems would need governance structures that could survive political changes. What would happen if participating nations disagreed about message, content, or priorities? How would humanity resolve disputes when the consequences might affect our standing in a galactic community? The institutional frameworks developed for beacon governance would likely shape humanity's approach to space.
What is going on?
The precedents established would influence everything from asteroid mining to interstellar exploration. As construction timelines compressed and launch dates approached, humanity found itself transforming not just its technology, but its identity. We were no longer an isolated species shouting into the void. We were preparing to become citizens of a galaxy-spanning civilization. The implications extended far beyond the beacon itself. Every aspect of human society was adapting to the reality that we shared the universe. The second-order effects of contact were reshaping civilization itself. After the echo who we choose to be. 2 years after the first radio exchange with 3 Atlas, humanity stood at a crossroads that would define our species for millennia. The visitor had departed our solar system in early 2027, accelerating along its hyperbolic trajectory toward destinations unknown. But its message remained encoded in our databases and our collective memory, a blueprint for joining a galactic community we had never imagined existed. The decision before us was deceptively simple: build the beacon or remain silent. But the implications of each choice reached into every aspect of human civilization. 3 scenarios dominated policy discussions across the world's capitals. The conservative path advocated maintaining listening posts but avoiding any active transmission. Proponents argued that we needed decades or centuries to better understand the galactic community, better to observe quietly, learning about our potential neighbors before revealing our location. This approach carried obvious appeal. It was safe, reversible, and allowed humanity to develop on our own timeline. We could continue advancing our technology and building the foundations needed to engage as equals. But critics pointed out the costs of isolation. The beacon specifications from 3 Atlas represented technologies centuries ahead of our own. Refusing to engage might delay our advancement indefinitely. The participatory path proposed building a modest, carefully controlled beacon system. This middle course would establish our capability to join the galactic network. Without immediately committing to active participation, the technical requirements were significant but achievable. A distributed array of transmitters coordinated by quantum timing systems. The beacon would operate at minimum power levels initially, announcing our presence but not overwhelming nearby communication nodes. Governance structures would ensure that no single nation controlled humanity's voice. The ambitious path called for full commitment to interstellar communication within a decade. Proponents argued that the visitor's beacon specifications included time-sensitive requirements. If humanity wanted to join the galactic network effectively, we needed to move quickly. This approach promised rapid technological advancement and immediate access to knowledge. Early participation might provide humanity with advantages to solve our most pressing problems, but the risks were enormous. Full participation would make Earth permanently visible to any intelligence monitoring the network. We would be committed to relationships and obligations we couldn't fully understand. Withdrawal from the network, once we had joined, might prove impossible. The debate transcended traditional political boundaries. Progressive environmentalists found themselves aligned with conservative military strategists, libertarian technologists allied with international diplomats. The cosmic perspective had scrambled conventional political categories. Public opinion remained divided but engaged. Polling consistently showed majority support for some form of beacon construction, but with significant variations based on specific proposals. The most popular approach combined elements of all 3 scenarios, building beacon capability quickly, but activating it gradually with extensive safeguards. The Galileo project evolved into a standing program for techno-signature detection. Its expanded mission included monitoring for additional interstellar visitors and developing the scientific foundation for future contact scenarios. Funding mechanisms emerged from unexpected sources. Tech billionaires redirected investment toward interstellar communication. Nations that had never participated in space programs began contributing. The distributed nature of the required technology allowed smaller countries to make contributions. Legal frameworks continued evolving through international negotiations. The Outer Space Treaty's restrictions were extended to cover interstellar communication nodes. New protocols governed the sharing of alien technology and the distribution of any benefits. The question of institutional stewardship became critical. Beacon systems designed to operate for centuries required governance structures that could survive political changes. The precedent of maintaining continuity would determine whether humanity could be a reliable member. Scientific preparations accelerated regardless of policy decisions. Radio telescopes continued monitoring for additional visitors and the broader galactic network. Gravitational lensing experiments tested whether stellar focal lines could amplify signals. Prototype beacon components underwent testing in Earth orbit and at lunar Lagrange points. The technical challenges were yielding to human ingenuity, but the engineering timeline remained formidable. Full beacon capability would require at least a decade of focused development. Psychological support systems emerged to help individuals and communities adapt. Contact counseling became a recognized specialty, helping people integrate the knowledge that humanity was part of a larger civilization. Support groups formed organically, bringing together people who were struggling to find meaning and purpose. Educational curricula evolved to prepare students for a future that might include interstellar communication. Children began learning mathematics and physics with the understanding that they might use these tools. The generational divide was striking. Older adults often struggled with the implications of contact, while younger people adapted quickly to the idea of galactic citizenship. Children seemed almost unsurprised by the revelation, as if they had always known and were merely waiting for adults to catch up. As the decade progressed, humanity's choice crystallized around a fundamental question, a question of identity. Were we explorers or preservers? The answer, when it came, reflected both impulses. Humanity would build the beacon, but carefully. We would join the galactic community, but on terms that preserved our autonomy. The compromise satisfied neither the most ambitious nor the most cautious, but it reflected a species-wide consensus about who we wanted to become. The night sky looked different now. The points of light that had once seemed distant and lifeless were revealed as potential homes, homes to intelligences whose messages might already be traveling toward Earth. The cosmos had become a neighborhood, vast beyond comprehension, but no longer empty. In the end, perhaps that was 3 Atlas' greatest gift. Not the technology to join a galactic civilization, but the knowledge that we had never been alone. Somewhere among the stars, other minds were asking the same questions, facing the same challenges, reaching toward the same distant lights. The conversation that began with humanity's accidental radio leakage was far from over. It was in fact just beginning. The real question wasn't whether we would join the galactic community, but what kind of neighbors we would choose to be. As Earth's first interstellar beacon powered up for its initial test transmission, a quiet carrier tone stepped upward through prime number frequencies. Our species' first intentional words in a conversation that had been waiting for us.